Lecture 15, we are going to continue our theme of the week, which is really extreme weather. And so today we're going to be talking about hurricanes. So as a quick reminder, quiz 8 is available from 6 p.m. today until 11 a.m. on Tuesday. So take the opportunity to have a go at that. So let's have a little bit of a review from Tuesday. Tuesday wasn't too complicated in terms of the concepts. It's just a bit of new content for us. So first of all, we talked about lightning. And really, the formation of lightning is still very much a mystery to us. We still don't have a terribly clear idea of what is actually going on in those clouds. Because first of all, lightning happens really quickly. Second of all, it's very difficult to predict where it's going to happen. There's sort of one particular location. Thirdly, you really don't want to be near a lightning strike when it happens, and so it can be a bit difficult to study this process. But in general, we think there are 4 things going on. We have charge separation. We get a different part of the cloud becomes positively charged. The base of the cloud becomes more negatively charged because we have hail that falls through the cloud, and as it falls, it collides with other ice particles and sort of takes electrons from those ice particles. We then have built up enough charge that a small portion of the air at the base of the cloud becomes incredibly highly charged, and once that happens, it tends to jump. It takes these steps in sort of 50 meters, 50-yard jumps at a time. And what it does is it spreads out in all directions. It's trying to find a path to the ground. And once that step leader gets close enough to the ground, you saw that really eerie phenomenon that happens, is that the ground responds by giving out these positive streamers, these positively charged sort of streamers. And then once they connect, that step leader and that positive streamer, then we get our lightning strike. And it isn't just one flash. We actually get several pulses often that make up the lightning strike, but it's so fast that we don't necessarily see those individuals. And remember that sort of flow of current massively heats up the air. It heats it up to ridiculous temperatures, and that air expands, and it expands so fast that it gives out this sound wave, this sort of basic, like an explosion, and that's the sound that we call thunder. So we then talked about how we go about developing these thunderstorms, and we had 2 different types. We had air mass thunderstorms and severe thunderstorms. So these are our little air mass thunderstorms. They're not particularly damaging, and they tend to pop up and dissipate relatively quickly. They're just little individual cells. And so we have 3 stages. The developing stage, we have this updraft. It pulls, we get sort of localized heating or localized convection going on, and so we get air rising up, forming an updraft. And as that air rises, it expands, it cools, we get condensation of water vapor, and that air continues to rise, especially if it's unstable air, it will continue to rise. And after a while that we've been sort of keeping that updraft going, we've built up our cloud, we've given it enough time that we've collided together cloud droplets and rain droplets, we've created precipitation, and precipitation starts falling out of one part of the cloud. And associated with that precipitation, we get this downdraft, this cold air that sinks along with that precipitation. And so we get this sort of cold downdraft instead. And if we give it a little bit longer, we get to our dissipating stage, whereas now the cloud is precipitating out of the whole of the base. And what that does is that we now have downdrafts over the whole of the base, and it cuts off the updraft that was feeding new, nice, warm, moist air into that cloud, that was building that cloud. And so that cloud just sort of gradually dissipates, it ends up evaporating away. And so these pop up just within air masses. They're relatively small, they're not at a front or anything like that. Then we have our severe thunderstorms, and we talked about the 3 different types that we can get based on more or less their geometry, their shape. First of all, we have these mesoscale convective complexes. We call them MCCs, it's easier to write. And these are basically just circular, and they're made up of lots of little individual thunderstorm cells. And the trick is that these severe thunderstorms, they're much, much stronger, and the presence of one cell tends to create another one. And so they can be self-perpetuating. They can last for much longer. Not each little individual thunderstorm, but that complex in general can last for much longer. We also have squall lines, which are these linear patterns of thunderstorms. And they form ahead of the cold front, in sort of between our cold front and our warm front, as these mid-latitude cyclones move through quite often. And they're 500 kilometers ahead. And again, this presence of this sort of cold downdraft spreading out along the base forces surrounding warm air to rise over that cold downdraft, and that initial sort of push to get that air rising itself creates another little line of thunderstorms. And so this sort of moves ahead of that cold front through time. And then lastly, our really cool ones, we have our supercells. And these are really very large, but they're just one cell. They're sort of 20 to 50 kilometers, and they're just one cell. And what really characterizes these is the rotation. And that's why these tend to be very, very intense storms, and they also tend to be much more likely to spawn these tornadoes because they have that rotation. They have these really strong updrafts that can create our tornadoes. And so to create our really severe thunderstorms, we need three things. We need a moist lower atmosphere, because we want that air to be able to condense, or so the water vapor in the air to be able to condense and create our thunderstorms. We need an uplift mechanism. We need to get that air going up to begin with. And then we need wind shear. We want wind to go in different directions and at different strengths. And this is going to be very different from when we talk about hurricanes today. Because with hurricanes, if we have strong wind shear, we don't get hurricanes. So that's one of my favorite exam questions. Okay, so make a note, mental note. We'll come back to it. And then we talked about tornadoes, which are amazing things. They're horribly dangerous. They're very, very destructive, but they are just really beautiful and very powerful demonstrations of how sort of powerful that atmosphere is. And so we need, again, three things for our tornadoes to form, and they're all somewhat interrelated. But unless we have all of these, we don't get our tornado forming. So first of all, we need nice, warm, moist air mixing with cold, dry air. And that means that we can have uplift. We have sort of unstable air, so we're likely to build clouds and thunderstorms. We need that wind shear. We need to create this either horizontal vortex or this spinning vortex, because that's what creates our tornado, this rotation. And we need unstable air, and a measure of how unstable that air is called CAPE, the convective available potential energy. Basically, how strongly will that air sort of lift, how unstable is that air. So all of those things go into creating our tornadoes. And do you remember, when we have this horizontal vortex, if we can create an updraft, we can bend that vortex so that one part is going upwards, then that's when we can create our tornado. And as we stretch that vortex upwards, it also stretches downwards, and that tornado can reach the ground. And we also have a corresponding downdraft on the other side, where that vortex returns back to its sort of horizontal position. So I want to check that you took on my survival tips from Tuesday. So tell me, let's see how many people we kill off this time. Where would the safest place to be in a house during a tornado? Where would the safest place to be? Where would be the safest place to be? Okay, let's see how many people we still have in the class. 78% or so, the majority. Okay, so 5%, 16 people went into your car. Not a good idea. Why is it a good idea to be in your car for another occasion? Lightning. If there's lightning around, a car is a safe place to be, because if that lightning strikes your car, that current will run around the outside and ground, okay? But you don't want to be necessarily in your car in a tornado. There's lots of nice airspace under your car. The winds can get under that and carry it along, okay? So don't get in your car if there's a tornado around. But Either A or B would work. If you don't have a basement, an interior bathroom is a good place to be, but otherwise a basement is a very good bet, okay? The southwest corner of the structure is a little bit of a myth, okay? It's something that people have heard of, but again, it's a myth. So really, if you have an option of getting into a basement, that's where you should go. So those are my tips. So remember, get somewhere low, ideally a basement or an interior bathroom. If you're outside, lie down on the ground, be as flat as possible so that no air can get underneath you. If you can, cover yourself with something like a mattress, and that stops flying debris from hurting you. Don't try to outrun one. It can go way faster than you can, okay? So don't do that. So you now know how to survive a tornado, a lightning storm. So let's see what we can do about hurricanes. And my top tip for surviving hurricanes is we can see these coming. They're huge. If you get told to evacuate, you evacuate. Okay? That's my top tip for hurricane survival. So what we're going to do is talk about what these enormous sort of atmospheric features are, how they form, what they look like if we sort of look under that cloud cover, what's the structure of these, and then we're going to talk about the damage that can be done. And in particular, we'll look at a number of case studies today and look in each example about what happened when that hurricane hit. What was it that did the real damage? What should you be most scared of if a hurricane is heading your way? So does anyone know which hurricane this is? Katrina, absolutely. If you recognize the Mississippi Delta there at the top of my image. So this is Katrina, and we're going to spend some time looking at that one later today. And I realized, horrifyingly, that you were about like 9 when this happened. Is that right? Very, very young. Oh my goodness, I'm aging fast. So, but anyway, hopefully you more or less remember it still. So we'll take a look at that example. So first of all, we have to deal with a complicated thing about the names of these things. So in the Atlantic and the Eastern Pacific, so just off our coastline, if we get one of these things, we call it a hurricane. If you are in the West Pacific, so closer to Asia, you call it a typhoon. If you are in the Indian Ocean, or if you're in Australia, you call this a cyclone. They are all talking about exactly the same thing. We've just given them different names in different parts of the ocean. The formation process is exactly the same. The structure of them is exactly the same. The damage that they do is exactly the same. We just give them slightly different names. So today I'm just going to use the word hurricane, and you can use that to sort of describe all of these things. So what are the characteristics of my hurricanes? They're about 600 kilometers wide. It sort of varies, but that's still only about 1/3 of the size of our mid-latitude cyclones. So those mid-latitude cyclones occur more often. They can be less damaging, but those mid-latitude cyclones are enormous. They're really, really huge. Hurricanes have a lot of power, and they're in that sort of smaller area. There are very, very large pressure differences between the inside of the hurricane and the outside of the hurricane, and so we get really, really strong winds. But unlike our mid-latitude cyclones, we don't have fronts associated with these. And that's because unlike our mid-latitude cyclones, where these are forming where we have cold and warm air, these are really forming in places where we have just warm air. And so we don't tend to have fronts associated with these things. But once they develop, and as they develop, they last several days. From that first initial sort of tropical depression up until sort of full hurricane and then dissipating, it can take several days for that process to happen, and so they can travel quite a distance in that time. So, we've been talking about cyclones. These are a type of tropical cyclone. So tell me, thinking back now to before the midterm, a long time ago, which two of these diagrams show cyclonic flow? Which two of these diagrams show cyclonic flow? A little bit dodgy. Okay. So we still do have a majority though, and as usual, the majority are correct. Okay? So you don't need to worry about whether it's going clockwise or counterclockwise or anything else. Remember that When we talk about cyclonic flow, we're talking about low pressure systems. So when we talk about hurricanes, when we talk about mid-latitude cyclones, when we talk about typhoons, all of these are low pressure systems, okay? If we talk about anticyclonic flow or anticyclones, these are high pressure. So it doesn't matter which way it's rotating, they'll rotate different directions in the northern hemisphere and the southern hemisphere, but if it's around a low pressure system, we call it cyclonic. So I just wanted to emphasize that point. So how do we get our hurricanes? How do we start building our hurricanes? So the first sort of birthplace of our hurricane is what we call a tropical disturbance. So it sounds pretty minor so far, and it's basically just a small cluster of thunderstorms, just like we talked about thunderstorms on Tuesday. And those thunderstorms can simply form because they're in the tropics, they're close to the ITZZ, we have lovely warm, moist air that can rise and form these sort of thunderstorms. We also get something called an easterly wave, and my diagram here shows that easterly wave. And what this is a little undulation, so a little sort of wave, basically, in those normal easterly trade winds. And you can see that as that wave occurs, what we're doing is we're converging air at the surface. So here's our easterly trade winds at the surface, and if we get a little bend in it, what we're doing is we're forcing that air together. And so as we force that air together, we have convergence, and that forces air to rise. It's one of our uplift mechanisms. And so this is a common way that we develop these tropical disturbances that can, not always, but can develop into larger hurricanes. So for the east coast of the US at least, where we tend to get our big Atlantic hurricanes forming is often off the coast of Africa there. That's often where we form some of our tropical disturbances, and then they travel across the Atlantic and impact the US. But really, we can start forming these little depressions anywhere along that sort of tropical area. So here's our easterly waves and our beginning of our hurricane. From a tropical disturbance, a certain number of those tropical disturbances get a little bit more organized. And as they get a little bit more organized, we call them a tropical depression. So the difference between a disturbance and a depression is that we now develop this central low pressure, and that thunderstorm, that sort of little cluster of thunderstorms starts rotating around that central low pressure. So we're starting to get this rotation going on that characterizes our hurricane, okay? If our tropical depression continues, if it strengthens, and not all of them do, if that continues and strengthens, then we call it a tropical storm. And to be classed as a tropical storm, we need winds that are 37 miles per hour or stronger, okay? And at this point, we give it a name. So we can keep track of it, we can issue warnings related to that particular storm. A certain number of those tropical storms will strengthen even further, and they'll become hurricanes. And to be classed as a hurricane, you have to have winds stronger than 74 miles an hour. And you'll notice that they're always really random numbers for miles per hour, and that's because we're scientists and we should be thinking about kilometers an hour, right? And so hurricanes are actually classified as hurricanes once they get stronger than 125 kilometer per hour winds, okay? So either way, whichever you prefer to think about that. And we then separate those hurricanes into 5 different categories. So you've probably heard that Hurricane Katrina at times was a Category 5 hurricane. So really, really strong hurricane, okay? So naming our tropical cyclones and our tropical hurricanes. So hurricane names, we actually plan this a long time in advance. And so we have our lists of hurricane names for sort of 6 years, and then they get recycled again. And so we start with A, and then the next tropical storm that forms has a name beginning with B, and then C, and then D. And if we get all the way through to Z, then we start calling it alpha, beta, but there's very few seasons where that actually happens. And so have a look and see if your names are on here anyway. I will show you some of those names. So first of all, have a look over here. We have a 60% chance right now of a tropical cyclone formation occurring just down sort of south of the Baja California Peninsula. So we're going to keep an eye on that, and I'll post little updates about that on the Facebook page. In the Atlantic, we still really don't have anything going on. No tropical cyclones at this time, and that's because it's still really very early in the season for tropical cyclones. Later this summer, there'll be much more activity in the Atlantic. So let's have a quick look at cyclone names. So here we have the Atlantic names. So anything that forms in the Atlantic, our first tropical cyclone of the year is going to be Tropical Storm Arthur. And then it will become Hurricane Arthur if it gets there. So can you spot any of your names? We've got Hurricane Kyle, Hurricane Laura, potentially. And so you can see that we have these different names for 14, 15. You can also see A, B, C, D, E. It alternates between male, female, and then female, male. And then we'll recycle them. If you're looking at the East and North Pacific, then we're going to have Hurricane Amanda would be the first one of this year, okay? And then Boris, and then they'll recycle. The ones in the North Pacific, further over towards Asia, have slightly different names, and there's only 4 lists of those. But we can also retire hurricane names. And we tend to retire hurricane names if they're particularly damaging, and especially if they cause significant numbers of deaths. Out of respect for the victims of that hurricane, we don't use that anymore. So Katrina, there were several Hurricane Katrinas, but we are not ever going to have another Hurricane Katrina. That name has been retired. It will no longer be used. Hurricane Sandy is not one that is going to be used again either. So we have, through time, retired some of these names and added new ones in. Okay. So let's think about where our hurricanes form and where our tropical cyclones form. So here's a map showing all of those little red dots are places where we've had hurricanes and cyclones and typhoons. And so you can see that we've sort of shaded in sort of orangey red the areas, that zones where we get hurricanes. And you can see that they're actually very defined zones. And so we can come up with some very good reasons for why that is the case. So the first one is that they are tropical. These are incredibly powerful storms, and they need a lot of energy in order to form. And so we need to be forming these things over extremely warm water. And I mean extremely warm water, so 27 degrees Celsius or more. That's really, really very warm. I think that's sort of high 80s, low 90s Fahrenheit. I'm still not quite good at my conversions. But that's really very, very hot compared to, say, the ocean off California, which is maybe 13, 14 degrees Celsius right now. It's pretty cold in comparison. And that's because these tropical storms, these tropical cyclones, hurricanes, are fueled by latent heat. So we have evaporation and sort of lots of water vapor above these really warm waters. And if we can get that lovely warm, moist air to rise, then we hit a point where it cools to saturation and we get condensation. And is energy released or absorbed when we go from water vapor to liquid? Thank you. And thank you. Yes, it's released, right? Do you remember that's why we start cooling down less, only 5 degrees Celsius per kilometer, as that saturated air continues to rise. So once we get condensation of that water vapor back into liquid droplets, it releases a huge amount of latent heat. And do you remember it takes enormous amounts of energy to get that water to go from being a liquid to a gas to begin with. And so it also releases a huge amount of energy when it goes from being gas back to liquid. And that's really the energy source for these enormous hurricanes. It's simply the condensation process, okay? And so the challenge next week in discussion is you're going to work out how much energy is actually involved in just one single hurricane in one day. And we're going to compare that to, say, how much we use here in the US, okay? So in any case, you can see that we need that warm ocean water, and we tend to get that closest to the equator. But also, on the western side of our ocean basins. Why do you think we have especially warm water on the western side of our ocean basins? So think back a couple of lectures now. When we talked about El Niño and ENSO, why did we have warm water on the western side? Why did we have all of our warm water on the western side of the Pacific? We have our easterly trade winds, right? We have our easterly winds either side of the equator, and that's blowing that nice warm surface water to the western side. And that caused the upwelling on the eastern side of South America. Is this vaguely ringing a bell? It's only a week or two ago. Okay. So you can see that that's really where we tend to get a lot of our hurricanes as well, where we have that super warm water on the western sides. So if we look at a map of what our sea surface temperatures are, this is what it looks like. And you can see that those redder colors represent that really nice warm water, and it tends to be on the western side, and that's really where we get our strong hurricanes. And especially you can see that really the warmest water is in that western Pacific. And that's why the sort of coastline of Asia along there is really impacted by an awful lot of typhoons, and those typhoons can be extremely strong because of this energy source of that lovely warm water underneath, much more so than perhaps the Atlantic. Okay, so the weird thing is look, our water is lovely and warm right at the equator, but we don't get hurricanes or tropical cyclones or anything else forming at the equator. And why is that? Because we don't have Coriolis force. So when we think of hurricanes, we think of this rotating, this sort of spinning storm. If we don't have the Coriolis force, we're not going to get that rotation, so we're not going to develop our hurricanes. Okay? And so if we look to sort of 5 degrees north and south of the equator, we have this band where we just really don't get these hurricanes. And it also means that they don't tend to cross the equator either. Okay? So we have too little Coriolis force around the equator. The third thing is that we need unstable air. And this comes back to that same idea about sea surface temperature. Where we have warmer air, it's more likely to rise. As that air rises, we get condensation. If we have lots of moisture, lots of warm air, it's going to be very unstable. We're going to be able to get it to rise, and we're going to be able to keep it rising. And so we can develop these thunderstorms. So definitely the western sides is where we get that. And then lastly, remember what I said my favorite exam question was. So for tornadoes, for these supercell thunderstorms to form, we really want there to be strong wind shear. We want there to be different directions of wind moving at different speeds, at different heights in the atmosphere, or in different directions. If we want a hurricane to form, and I know that's a strange thing to say, but if we want our hurricane to form, we don't want there to be wind shear. Because really what we want is to concentrate all of that energy that is being released as latent heat energy. We want it all to be in the very middle, okay? Because as that energy is released, it warms the surrounding air. That air is forced to rise even further, and that pulls in more air, okay? It basically strengthens our hurricane. If we have really strong winds up high in the atmosphere, all of that air is spread out. And so we might still get condensation, we might still form clouds, but that energy is going to be spread out in different places. It's not going to be concentrated in the middle, and so it's not going to strengthen our storm. Does that make sense? Mostly? You guys are really hard work today. Okay, so tell me then, if you won't answer me verbally, tell me, when do you think the peak time for hurricanes in the North Atlantic? When will be the peak time for hurricanes in the North Atlantic? So think about those 4 factors that we just talked about. Right, let's see if we agree. We do, or at least 70% of us agree. So why did you put August, September? Because it's warmer, absolutely. There'll be warmer water at that point in the Atlantic. It's had the summer in order to warm up that water, and so there's going to be more energy, more moisture in the atmosphere available. So tell me, When would we get cyclones off Australia? Same proportion again. So still 69% agree with me that we would most likely get strong cyclones off Australia in January, February. And that's again because that's when the warmest waters will be there. That's their summer, remember. We have these opposite seasons going on. Okay, so what does a hurricane look like? So you can see, everyone's seen these big satellite images showing that we have that central eye, and then we have this sort of cloud cover over the top. And what that's hiding is it's hiding what we call these spiral rain bands. If we look sort of at the internal structure of our hurricane, then we do have our central hurricane eye, which is this central part here, okay? But then we have, basically we have these bands. It's not consistent cloud all the way out. We have a really strong band here, we have a band here, and then we have a band here. And those are spiraling inwards in that counterclockwise direction in the northern hemisphere, and then it would be clockwise in the southern hemisphere. And this is showing you what the air is doing. So remember that we're a central low pressure in the center of our hurricane, and so air is moving from high to low, it's moving from the outside in, and then it's being deflected by that Coriolis force so that it spirals inwards. And then in the very center here, this is where we have air that is being forced to rise. So initially it rose just because we had that convergence, or we had our thunderstorms forming. Now we have the central low, and air by convergence is being forced to rise. As it rises, it's also spiraling, and so this band either side of the eye is where most of that rising air is moving. And as it rises, it cools condensers, and so this is where most of that latent heat energy is released. And so that warms the air in these two columns here, and it forces it to rise even further. So it sort of strengthens that upward pull of movement. And then as we get up to the top, we can see that now we have air spreading out in all directions at the top. Okay? And so we also have air sinking a little bit in the eye, which is why it looks clear. So if we look at that in a graph form instead, you can now see I've sort of taken a cross-section of my hurricane. We have the eye, what we call the eye walls. These are the two big columns either side of the eye, the two big columns of cloud. And then again, we have a sort of clearer patch, and then another spiral rain band, a clearer patch, a slightly weaker spiral rain band. Okay? And so you can see under here, I've also shown what the rainfall is like in this smaller rain band. There's sort of moderate rainfall, and then it slackens off a bit. Then we get heavier rainfall, slackens off a bit, even stronger rainfall. And then in the eye, it's that calm in the eye of the storm. We don't really get any rainfall in that central eye. And then we see the same thing on the other side. So down here, you can also see what the pressure does as you move through the storm. And you can also see what the wind speed is as you move through the storm. So tell me, where would you experience the highest pressure? So if you look at my little diagram there, where in the hurricane would you experience the highest pressure? We have a little bit of a debate. So some people say the eye wall, some people say the outer edge. Turn to your neighbor, turn to the person behind you. I'm going to see if we can break the tie. So tell me, where would you measure the highest pressure? Okay. Well, there's a slight shift. Am I asking about the highest pressure or the strongest pressure gradient? I'm asking about the strongest pressure, the highest pressure. If you look at my little graph in C there, where does it say you would measure the highest pressure? Where's the highest value that you would measure? It's here, right? Here's high, here's low. So this is where you would measure the highest pressure. It's that very outer edge. Okay? A lot of people are thinking it's the eye wall because this is where there's the biggest change in pressure. Okay? So we have that really strong low right in the middle. But don't get caught out between the difference between the strongest or the highest pressure and the strongest pressure gradient. That strongest pressure gradient is going to cause the strongest winds. Okay? So where would you experience the lowest winds? So let's give this one more go. So if you look at my bottom diagram, where would you experience the lowest winds, the slowest winds? Okay. That's better. I would agree with you, yes. If you look at the wind speed, then yes, it's going to be relatively low at the edges. It gets faster and faster and faster as you come towards that eye wall, which is really the most intense part of the hurricane. But then look, that wind drops to more or less zero as you go into the eye of the hurricane, into the calm in the eye of the storm, remember? Okay? So I will set a couple of quiz questions on this, given that it seems to be a challenge. So first of all, I wanted to show you this really cool photo. So this is a photo taken by some military planes that actually flew into the center of Hurricane Katrina. And what you can see on the other side, they've just entered into the eye of Hurricane Katrina high up. And so on the other side there, what you're seeing is the eye wall. Isn't that a cool photo? I think it's amazing. And so these guys, they're called, I think they're crazy, but they're called hurricane hunters, I think, and I think there's even a show about it. These guys take their planes and they're packed full of scientific instruments, and they fly into hurricanes so that they can measure what's going on, and so we can understand more about the processes going on within our hurricanes. And this is, I think, one of the most spectacular photos I've ever seen of this eye wall. We can also observe hurricanes using radar. We've talked about this a couple of times now. We give out pulses of radio waves, and if there are things in the atmosphere, bits of like cloud particles or sort of droplets of moisture, then we get bounce back. Those radio waves bounce back, and we can tell by how much of that wave bounces back how much material is in the air. And so this is a really beautiful image that really shows you those spiraling rain bands. So those orange and yellow colors show you where you have intense precipitation, and you can really see them beautifully spiraling inwards in that counterclockwise. So here's our different hurricane categories. So just like we have the Fujita scale for tornadoes, we have the Saffir Simpson scale for hurricanes. And these are probably ones that you've heard of if you've heard the news when we talk about hurricanes. So category 1 is the least powerful of our hurricanes, and you can see that the pressure in the center isn't particularly low. As we get towards our category 5 hurricanes, these really strong hurricanes, you can see that pressure, that central low pressure, gets lower and lower and lower and lower, so it's pulling that air in really much stronger. If you look at the wind speed, you can also see that as we go from category 1 to 5, our wind speed really does pick up a huge amount from, say, 74 miles an hour, which is pretty damaging in itself, up to greater than 155 miles an hour, which is immensely powerful, and not a lot will be left undamaged in winds like that. We also have storm surge. We're going to talk about this in a second. This is what happens when that wind forces water ahead of it, and it basically lifts up the surface of the ocean, basically just like winds drive waves. It lifts the surface of the ocean, and the more and more intense hurricane you get, the larger that storm surge is, until you reach maybe about 6 meters. And so I know that you don't work in meters, so I'm about 1.5 meters. So if you imagine 4 of me, so 3 more of me stood on top of myself, that is a 6-meter storm surge. That's a huge amount of extra water coming in at the coastline. So we'll talk about that more in a second. So you can see that, unsurprisingly, we go from not so damaging to really catastrophic. Category 5 hurricanes really don't leave much behind, and we'll take a look at some images of that in a second. So what should you be scared of if a hurricane is coming towards you? Okay? So which of these 4 would you be most scared of if there was a hurricane forecast to come your way? I'm going with my friend at the front. He said storm surge. Definitely. Okay? If you live near the coast and a hurricane is coming your way, it's windy, yes, and that can cause damage, and it can sort of damage your house. But really what you should be most scared of is that the storm surge is on its way. Okay? And we'll take a look at that in a second. So how do hurricanes cause damage? First of all, it's really windy. And so that wind can do damage to structures, it can pull down trees. An awful lot of trees were damaged during Hurricane Katrina. Tornadoes, where hurricanes make landfall, so where they first hit the coastline, we do get little tornadoes forming. They don't tend to be those really powerful ones, but we do get some tornadoes. We get really heavy rain, and I mean really heavy rain. So if you look at the peak rain rates, you could get up to 8 feet of rain a day if you sort of had that rain rate over a whole day. If you put that in comparison, we probably have that much rain a year. Okay, so that's a huge amount of rain. And so that causes very severe flooding, especially if you have your storm surge on top of that. And it can lead to landslides, everything else. When we have that very heavy rain, you know that we get landslides in California as well. And then lastly, we have our storm surge. And it can be really, really devastating. If you're being evacuated, if you're at the coastline, you really need to move. So what causes our storm surge? So first of all, and I think this is really cool, if we have a low pressure system and a really strong low pressure system, then we have less weight pushing down on the ocean surface. And so the ocean surface rises up a bit. I think that's really fun. And so here is a little graph showing you the different pressures for Hurricane Katrina as it moved onshore. So for every 1 millibar drop in atmospheric pressure, then we see a sea level rise of 1 centimeter, something like that much. Okay? So my challenge for you is, so if you look at that map, work out how much pressure drop we saw from the edge to the center of that hurricane. How big would the storm surge be due to that pressure difference? Okay? So look at those isobars. Consult your neighbor. I think that's close to everybody in the room. So let's take a look and see if we agree again. 50% of people agree with me this time, and I would agree with them. Because what's the pressure on the outside in millibars? 1004. What's the pressure in the middle? 984. What's the difference between 1004 and 984? 30 or so. Okay? I know I had a lot of people in the exam that put 1024 minus 1008 equals 1000 and something. So just be careful of things like that. So yeah, so we would have just the pressure difference alone between the outside and the center of our hurricane means that there's less pressure on the ocean surface. It would have risen by 30 centimeters, which is like that much, like a 12-inch ruler, okay? But how big did I say the storm surge could be? A lot bigger than that, right? Can you see on the trees where the bark is stripped off? Yep. You see those arrows there? That's how big the storm surge was where Hurricane Katrina came ashore. Is 30 centimeters explaining that? No. This was a huge storm surge, a really enormous storm surge. And you could see this all along the coastline. You could see the bark was stripped off the trees where that storm surge hit. So the main reason that we have these really strong storm surges is the winds. Okay? And we're going to look again at an example of sort of Hurricane Katrina. So you can see that we're in the northern hemisphere. We're going around a low pressure, and so we have counterclockwise movement of the winds. Okay? So that hurricane is moving northwards. Its path in general is moving this way towards the land. Okay? And then let's look at our winds. So remember that our winds are spiraling inwards in this direction. And what that means is that on this side, our winds are moving in this direction. We're going counterclockwise. Our winds are also moving towards the land. On this side of the hurricane, remember we're moving counterclockwise still. These winds are actually going to be blowing the other way. They're going to be blowing away from the land. And so what we have to do is we have to think, as that hurricane moves towards land, on this side, we're going to have both that movement of the hurricane and the winds blowing towards land, we're going to get a really strong storm surge affecting this part of the coastline. On the other side, we have the hurricane moving and driving water ahead of it towards land. But if we look at our winds, they're really blowing away from land. So on this side of our hurricane, we're going to have much less of a storm surge than on the other side. Does that make sense? Yes? No? Yes, good. One person at least. Okay, so let's take a look at Hurricane Katrina. So this caused about 1,836 deaths, caused $81 billion worth of damage. That's a really huge amount of money. So in many areas, we don't necessarily think of it. We think of it as something that happened in the past, but really a huge amount of the coastline is still really very devastated down there. It's taking a long time for recovery. So our little hurricane started as a tropical disturbance and then a tropical depression because of our little easterly waves. This time it wasn't off the coast of Africa, it was actually to the south and west of the Bahamas, so much closer towards the US. And it was the 23rd of August. On the 24th of August, so relatively quickly, it had strengthened to become a tropical storm, and so its name was Katrina, okay? And so, the 25th of August, this is when it strengthened to become a hurricane. It was a relatively weak hurricane at this point. It was a Category 1, and you can see it's just about to move towards the coastline of Florida. And you can see at this point, it doesn't necessarily have that beautiful hurricane sort of central eye that we often think about when we see those really well-developed, enormous hurricanes. But it still had a huge amount of power behind it. It caused $600 million worth of damage, not insubstantial, and up to 9 deaths, okay? The problem is that as it moved across Florida, it moved into the Gulf of Mexico. And if anyone has ever been to the Gulf of Mexico on holiday, you know that the water is really lovely and warm. And so all of a sudden we have this lovely warm water, and in 2005, which is when this hurricane occurred, there was very unusually hot water sitting in the Gulf of Mexico. And that basically just fueled that hurricane, and it really strengthened. It became Category 3. At this point, we were getting seriously worried. And so we started issuing mandatory evacuation orders for much of the coastal cities along the Gulf Coast. And this shows the sea surface temperature and just how warm it was. And you can see that as it's moving off Florida, it's really strengthened. You can really start to see those spiraling rain bands, and it's sort of heading towards warmer and warmer water, which was a concern because, again, we can see this strengthening as it continues. So by the time we hit the 28th of August, we now can see our beautiful eye in the center of the hurricane. We can see these spiral rain bands, and it strengthens to become a Category 5 hurricane, a really, really very strong, large hurricane. And so now the coastal cities were incredibly worried because we were forecasting something like an 18-foot storm surge, okay? So imagine your tallest friend, probably about 6 foot, times them by 3, okay? And we had sustained winds of over 175 miles an hour and extremely strong rainfall. And here is a lovely shot of the 29th of August. This is where Hurricane Katrina is approaching Mississippi. And we were lucky. And in particular, New Orleans was very lucky. Because what happened was it managed to weaken a little bit. Instead of being a Category 5, it was a Category 4. But still, those really strong winds during the time it was a Category 5 were pushing that water ahead of it. And do you remember what we were talking about before, about the storm surge on this side being much larger than the storm surge on this side? So at some point, we thought there was going to be a direct hit on New Orleans. And what happened was it veered in this direction. And so it actually sort of hit land slightly to the west of New Orleans. And so New Orleans was spared the worst of that storm surge. It didn't end up saving them, unfortunately, but it could have been substantially worse. So what did Hurricane Katrina do? So there were very strong winds as it hit land. So we killed millions and millions of trees along this coastline. We got tornadoes forming all along that coastline again, from Florida to Georgia, Alabama, Mississippi. Extremely heavy rain, and that storm surge, you saw how big that storm surge was. In that worst affected part of the coastline, it actually reached 27 feet, and seawater moved 6 miles inland. Think of that, 6 miles inland. And so it was really incredibly devastating. So storm surges are not like tsunamis. They build through time. It takes time for them to build up. And so I have a little video to show you of some rather foolish guys. It's very good that they end up going out here, because otherwise I'd have no videos to show you. But still, it's not a good idea to do this. So here is the Hurricane Katrina storm surge. So these are guys that usually chase tornadoes, and they decided to go down and film Hurricane Katrina. And they're sat in their car at this point, and they're watching those waves being carried in. So this is as Hurricane Katrina is approaching land. You can see the strength of those winds, and you can see that wind being pushed ashore. They decided at some point, probably too late, that it was a good idea to retreat. And so they retreated to a nearby sort of motel, I think it was, and they continued filming. And a little bit later, the waters got a little bit higher. It's starting to come into the motel. Not a good sign. Okay. A little bit later than that. Now the water's still even further. At this point, they have sort of cameras spread out. Now it's sort of getting to waist deep. And this is just in the case of sort of maybe 2 or 3 hours or so. The cars are starting to float. Now the cars have started making their way into the motel through the door, and you can see how damaging this would be to structures, because this is quite a way back from the coastline still. There's our car, and you can see the wind whipping that water outside. As we continue through time, deeper and deeper and deeper. And now they're on the second floor. And if we look out, plenty of furniture floating around. This is the view at the sort of the peak of that storm surge. So there's a whole story under here. Basically, that water has reached the second story. You can see how miserable it is outside. All of that wind is blowing that water. This is the central courtyard of that motel. And so they're sort of somewhat protected on one side. And they're probably somewhat regretting things at this point. It's not a good place to be. And then gradually that storm surge decreases again. And they're sort of able to get down, okay? But you can see that there's really strong winds at the same time. It's a miserable situation to be in. And this is why you don't want to be at the coast when this happens. Because this is what Katrina's surge did to this area of coastline, so near Biloxi. And this is part of the Weather Underground, and they do a whole series of what was along the coast here. So you can see that if we start looking at images taken of satellite images after this storm surge hit, you can see the damage to a lot of these houses. And in some cases, they're just gone. These ones at the coastline are just gone. You can just see the foundations remaining. And so there's a huge amount of damage, and these sort of entire communities wiped out. And so in particular, you can see boats were brought inland. This was a house at some point. You can see the steps up to it. You can see the debris left behind from that storm surge as it moved through the trees. And just entire houses are gone. And I think one of the eeriest things I've ever read is down here, where they say that there was a substation that was destroyed, and it was a receiving station for 911 calls. And they still get calls because of some weird electronic trick from areas like this, where there's nobody left, there's no house. They still get incoming calls for 911, which is, I think, really quite creepy. Okay, so on that note, so storm surge is not something to mess around with. It's incredibly powerful. So let's look at New Orleans, because this is what everyone heard about. This is where the damage was done. This is where a lot of those deaths occurred. And if you look at New Orleans, there's a reason why we were so worried about this city. Most of it is already underwater. And that's because it's built out on this Mississippi Delta, and we've been diverting the rivers, and those rivers would usually bring in sediment and replace that sediment. And we've built on it, and it's just been subsiding, it's been sinking downwards. And that's why we have these levees, we have these walls as built as flood protections on either side. And you can see that those walls are probably about 23 feet. And remember that the peak storm surge in parts of the coast was 27 feet, so that wasn't going to help us very much. And you can see that, unfortunately, as one of those levees gave way, that city flooded, and it flooded incredibly quickly. And again, unfortunately, we don't have time to watch the whole thing, but there's a pretty amazing video taken by a family. This was at 8:39 or so in the morning. You can see their opposite neighbors. This was about 2 hours later. That water rose incredibly fast, and you can see that these are single-story homes. And the problem was that people were caught out in this sort of situation. And you can see that there's a number of houses around here, and people were trapped. People couldn't get out, and unfortunately they drowned. And these guys, at least opposite, they managed to sort of sit out the storm on their roof, and then they managed to sort of find a boat over here and come across. But it's quite an amazing video to sort of see their perspective on just how quickly that water rose and sort of experiencing that storm. So, more cheerful stuff. So, everyone's heard of Hurricane Katrina. You can see the path it took there, and that sort of the redder the color, the more intense the storm. How many people have heard of Cyclone Nargis? It happened 3 years later, 2008, so you're probably old enough to... Has anyone heard of this one? No? So, they were both Category 4, and they were both Category 3 when they actually made landfall. You can see that Cyclone Nargis only had a 12-foot storm surge, but it still had really very strong winds. And just to let you know where we are in the world, this is India over here, this is Indonesia and Thailand over here, this is Myanmar. You might have heard of that. So do you remember we said that for Hurricane Katrina we had about 1,000 deaths, or 1,800 deaths, and we did about $80 billion worth of damage. If we're talking Myanmar, there's less infrastructure, but it's incredibly densely populated. Does anyone know how many people died in this cyclone? No? This was in 2008, remember? 138,000. 138,000, and we've never heard of it. Okay? And I think I wanted to make the point that here in the US, we have the forecasting, we do issue evacuation warnings, not that everyone goes, they should go, but they don't go. And we have the ability to move people. We also don't have enormous population densities. Especially around the Indian Ocean, there are countries that are incredibly low-lying. They're really close to sea level to begin with. They have really very high population densities, and they don't necessarily have the resources and infrastructure to move people terribly easily. So if you look at some of the most damaging hurricanes and cyclones, they tend to be in that region. And it's worth remembering that these things are powerful, and they are very, very, very dangerous. So tell me, if you look at these intensity images, those brighter colors occur when they're over the ocean. So why do these hurricanes or cyclones weaken so quickly? Why do they sort of dissipate and fade out when they hit land? So why do you think? Is it because mountains get in the way? Because energy is used up in destroying stuff? Is it because there's less moist air rising? Or is it because they're experiencing more Coriolis Force? So which do you think of those as the most likely reason for why they tend to die out as they hit land? Okay, let's see if we do better this time round. Oh, good, we do, hooray. It's a nice, good balance of the answers. So yes, the reason that these things die out so quickly when they hit land is because we're cutting off their power supply. Their power supply was this moist rising air, and then that condensation which released energy forced that air upwards and brought in even more air and lifted it. And so if we start moving that hurricane or that cyclone over land, it really does start to die out to a certain extent, okay? Because we no longer have that nice moist air that's rising, condensing, and producing energy. So if we take a look at the patterns of these hurricanes, you can see that there are quite specific paths that these things tend to take. You can't necessarily say for any one particular hurricane that it's going to follow the typical path, but in general, they tend to go what direction with our winds? Easterly, and then what happens is they tend to move towards the north. They go westerly again, okay? And so you can see that they follow this quite specific pattern. If we look at individual ones, so I'm going to show you the Atlantic hurricane paths for 2012, you can see that it tends to be a little bit more chaotic if you look at individual paths. But in general, they tend to follow this sort of easterly movement, and then as they move to the north, they tend to move more westerly. So can you see a good example of one that doesn't necessarily behave itself and actually started turning back easterly as it got pretty far north? And in particular, it affected the US. So can anyone think of a particular storm that affected the US in that particular location in 2012? Sandy. You are looking at the storm track for Hurricane Sandy. So here it is. It's not necessarily a typical pathway. It doesn't sort of form in this direction and go off here. Instead, it formed to the south. It strengthened, became hurricane strength over parts of the Caribbean. And then it started heading this way, but then it got bent backwards, and it actually struck close to New York, if you remember. Okay? So let's talk about Hurricane Sandy. So the first thing is, Hurricane Sandy was indeed a hurricane when it was in the tropics. Okay? It was a hurricane at that point, but as it moved north, actually some other stuff happened that changed it into something we call an extratropical storm, outside the tropics, extratropical. And you can see that at this point we have really low pressure here. This is our little symbol for a hurricane. And you can also see that we're starting to have fronts associated with it, which is not the case of our typical hurricanes. Okay? And I want to show you a really cool little video about why that storm in particular strengthened and so much. And so what happened was that Hurricane Sandy was moving up the coastline, and it got incorporated into a big giant mid-latitude cyclone that was also moving across the country. And what happened was they met, and they ended up merging together, and that created this really enormous system that usually wouldn't exist. So we were pretty unlucky in a way. And this guy at Columbia University created a really cool little animation. So watch this sort of hurricane as it moves up the coast, and you can start to see it connect with this sort of cyclone. You can see it as they merge together there, so you have to be quick. So here's the hurricane, here's our mid-latitude cyclone, and they end up looping together, and that's what created this really quite unusual, powerful storm, and it pulled that storm also towards the US, whereas usually they go out across the Atlantic. And so Hurricane Sandy was not that strong a storm. It was really not hurricane force by the time it struck the US again. But it was very late in the year, and it was moving up across the colder water, so it did become less strong. Okay? But it was a very, very intense low-pressure system. So the last thing I wanted to talk about today is really what is in our future. So what does the future have in store for us, given that we have climate change occurring? We are going to see further climate changes, and we're going to start talking about that next week and the week after. It's really not terribly clear what is going to happen to our hurricanes. It's very difficult for us to say that, say, Hurricane Sandy happened because climate change is occurring. We can't say that the enormous Typhoon Haiyan that hit the Philippines last year was caused, or earlier this year perhaps, was caused by climate change. We can't say that any one storm is caused by climate change. And that's because Yes, we are warming up sea surface temperatures an awful lot in some places, and that provides more energy for these storms. But we're also increasing the amount of wind shear that we see in parts of the atmosphere, not everywhere, but especially in some places where these hurricanes tend to form. And so we're really not very clear right now, and we don't have enough confidence to say for certain what will happen to the number or the frequency of our hurricanes. But really what we are expecting is that once these hurricanes form, it is somewhat likely that they will become much stronger than we've seen before. People are talking about by sort of 2100, if we have really the most change that we're thinking is possible, we're sort of seeing hurricane category 6 type hurricanes rather than anything else. And I think that's a certain amount of exaggeration, but certainly we might expect stronger and stronger hurricanes. And what we are very certain about is that the inevitable sea level rise that we are experiencing just due to the fact that warmer water expands and due to melting of ice on the land is going to make all of the coastal cities much more vulnerable to things like storm surge. In New York, really that storm surge only overtopped the coastal defenses by a small amount, but that was enough to flood enormous parts of the subway system. And so as we experience more and more sea level rise, cities like Miami in particular are getting very vulnerable. Okay, that's all for today. I will see you on Tuesday for pollution.